Please interrupt me. I'm going to go through this stuff a little bit quickly because I hear that it's already you've already read the Eclipse attack paper, and I've already looked at some of the peer-to-peer stuff. But Bitcoin uses the peer-to-peer network to announce transactions and blocks. It makes 8 outgoing connections. These are TCP connections initiated by the node. It makes up to 116 connections that are incoming, so they're initiated by someone else. And it makes 1 feeler connection under some circumstances. And I'll talk more about this feeler connection later. You can actually treat the feeler connection as an outgoing connection. It is an outgoing connection, but it has some different rules. So I just broke it out separately. But if you want to say that there's 9 outgoing connections counting the 1 feeler connection, you can say that as well. And I want to point out that when we talk about outgoing connections, we're always talking from the perspective of a node. So if you look at this purple node, it has an outgoing connection to this yellowish node. But from the yellowish node's perspective, this is an incoming connection. So whenever we talk about outgoing and incoming, it's really which node is it an outgoing one. Everyone's outgoing connection is another node's incoming connection. So nodes store the IP address of other nodes in 2 tables. The new table stores sort of like hearsay IP addresses. The node has heard that this might be another node that they could connect to, but they've never actually made an outgoing connection to that node. So it could just be total garbage. And in fact, it's pretty easy to fill the new table up with garbage. Give you nothing. It could give you just the stuff it wants you to know about. It decides what access you get. And this is referred to in the peer-to-peer networking world as an eclipse attack, or that this blue node is eclipsed. All right, so the first thing, so we're going to talk about later how you can eclipse a node. We're just going to, but for this, we're just going to look at what bad things can happen when you're in that position. So a malicious party, controls access to information to particular nodes. So one thing that can happen, is that if you were to partition a miner from the rest of the network, so you've stuck 30% of the mining power in a partition, and you're the attacker here, and you also have mining power, you have 40% of the mining power. Because these 2 miners don't learn about each other's blocks, they will build independent forks. And because this is 30% and this is 30%, if the attacker has 40% of the mining power, they can build a longer chain. So by partitioning the Bitcoin network, you can actually engage in what would be a 51% attack without majority hash rate. Another thing that you can do is you can partition, say, like a merchant and some mining power. The miner won't learn about the blocks that are being created over here, so the miner will create its own fork, and then you can double spend. So you can send a particular coin to the merchant. You can send that same coin to yourself. The merchant only sees this blockchain and only sees this transaction. They don't even realize there's a double spend. And then when you stop partitioning the merchant, the Bitcoin miner, their blockchain will go away, and this blockchain, they'll realize that this blockchain is the one with the most weight, and you've double spent. And notice in this case, you don't actually require any mining power yourself, because you don't require any mining power yourself because you sort of like use this miner to perform this attack by putting it in the partition. But this miner may just be an innocent victim that you've managed to partition. And some other bad things that can happen. A lot of layer 2 protocols, including Lightning, have this notion that when you see a particular transaction, you have an adjudication period to post a breach remedy transaction. And this security relies on the censorship resistance of Bitcoin. So it's assumed you see someone has posted an old transaction, you have the breach remedy transaction to post it. But if you're eclipsed, the eclipsing attacker could just censor that transaction. So if you're like a Lightning node and you're eclipsed from the Bitcoin network, you can break the security of Lightning. Lightning fundamentally assumes that Bitcoin is censorship resistant and you can announce your transactions. Right. So you could imagine an attack like you're talking about where I know your IP address and I also have a Lightning channel with you, and every time you announce I post an old Lightning state, you announce the breach remedy transaction, I just drop it on the ground. However, you can have situations where maybe the party that eclipses you is not necessarily malicious. They just may, and we've actually seen this happen. Chainalysis back in 2015 eclipsed a bunch of people and was just dropping their transactions on the ground, but like announcing transactions to them. And so it created a situation in which those people weren't able to announce their transactions. So it might be that the eclipsing party is not even in a conspiracy with the party that's cheating in the Lightning network. But yeah, you really want to make sure you're not eclipsed if you're using a Lightning if you're doing layer 2 stuff. What? So I think this is like a good question, because like normally in Bitcoin, it sucks if your transaction is censored, but it doesn't necessarily mean that you get cheated if your transaction is censored within a time frame. But with layer 2 protocols, we're now making that assumption. And so I think it would be good for people to think about it. Maybe the ability just to like a warning, and you export that transaction from your wallet and like post it to a block explorer, or some additional means. But yeah, I think it's like a good thing to think about, like what happens if someone were to actually try to apply this this attack at scale to Lightning Network. Maybe they go and just take a botnet and start attacking all the Lightning nodes and knocking them offline, and they hope they can knock enough offline that they can steal from someone's channel. But I think that's like an interesting project to look at. Privacy. If you are the only connection that a node has to the Bitcoin peer-to-peer network, and you announce a transaction, they know that that transaction came from you. So if they eclipse you, they can determine which transactions originated your node. And then a fork, you can imagine situations where, say, like, it's less common now, but you have like a 2-block fork in the Bitcoin network, right? And someone could just show you one side of that fork. So they could double spend a lot, and then if there's ever a 2-block fork, they show you the losing side of that 2-block fork with the double spend, and you think, oh well, I've got one confirmation on top of that, or 2 confirmations on top of that. That's good, but what you don't see is there's actually like, say, like a 6-block. The other fork has like 6 blocks in it. Does that make sense to everyone? So how can this happen? Onpath or Inpath attacks. I'm going to define what an onpath and Inpath attack is in the next slide. Off-path attacks that manipulate the peer-to-peer network. So everyone read the Eclipse paper. So the Eclipse paper is generally talking about off-path attacks that manipulate the peer-to-peer network. DNS attacks that poison the tables. So when a Bitcoin node to learn about the other nodes in the system use DNS, when it's first like booted up, when it has nothing in its peer tables. You can attack it that way. And then we'll look at some other bad things that can happen. So this Onpath, Offpath, Onpath, Inpath distinction is a network security distinction. Offpath, you're basically the attacker here. You can send messages to the victim. You can receive messages to the victim. But the victim can send messages to other people that you can't see. So you can't see these, and you can't interfere with their traffic. So normally the security when you just like connect to a website, you're an off-path attacker. You can't see the other transactions. You can't pretend to be other people in the network. And on-path, the attacker can send messages to the victim and receive messages from the victim, but they can't drop packets. So they can see the packets that get sent, and they can inject their own packets, but they can't actually drop packets. And then finally, an Inpath attacker, and this is usually what people think about with man-in-the-middle attacks, is that the attacker is sitting directly between the victim and the rest of the network. So the attacker can just, like the attacker sees a packet it doesn't like, it just doesn't relay it, it just drops it on the ground. And one of the important distinctions here between Inpath and Onpath is that Inpath is generally very expensive for attackers to do. They get like a lot of traffic, they have to like buffer this traffic and send it on, so they will introduce a lot of latencies. Whereas Onpath is much cheaper. You can just sit there, you can like tap a network line, see the packets coming through, and then inject traffic. So a lot of censorship frameworks will use Onpath for their like large amounts of data because it's just cheaper to do. And then when they really want to do a targeted attack, they'll move to Inpath. So a lot of the Great Firewall of China is Onpath, not Inpath. And if you look at the quantum insert, some of the NSA stuff, they were like on-path attacks. They see the traffic, they send new packets. So an on-path attacker can also eclipse you. And in Bitcoin, an on-path attack actually functions a lot like an in-path attack. Because Bitcoin is Bitcoin connections are TCP connections, you can send a packet that says like, I want to reset a particular TCP connection, and you can drop it. So you can inject traffic that will cause the host to break that TCP connection, and then they won't receive the packet. So it's kind of like you have this ability to drop things. The host still receives the packet, they just discard it because they think the TCP connection's been broken. But one of the things that you could do is you could put some sort of encryption here. It's a little bit tricky, but if you assume that you've set up keys, the attacker, I mean, I guess the question is, and here's a question for the room. If you put encryption here, how does it give you any benefit? Yeah, so I don't think encryption would help you against reset attacks. There is other things that you could do. For instance, you could forge packets, even though you're not in path. You still see the TCP like header information, the SYN cookies and whatnot. So you could generate packets from this host without actually being this host. And so you could say, rather than just send a reset connection and break the connection, you could send a message that would get that like IP address blacklisted. Personally, I think encryption doesn't help that much here, but it can limit some of the attacks. But probably what an attacker would want to do is just like reset this connection and have you connect to someone else. But if there was a reason, and I think this is like kind of an interesting question that needs more thought, is like how much does it buy you here? Is blacklisting an IP versus breaking a connection significantly worse for having encryption here? Yeah, so like maybe the attacker doesn't, you establish this encrypted connection and then the attacker shows up. But then the question is, if the attacker then disrupts this encrypted channel, and then is like, oh no, I switched keys, how do you tell between those states? And so it seems like for a targeted attack, that's not so good. But like, if someone was just like doing this at scale, then they'd have to like write software to do the crypto and like to disrupt these things, and then to make sure that your packet didn't get in first to like reestablish the key. So I guess I just leave this as an open problem for everyone to think about. Is if you did have trust on first use encryption here, or you had something like a VPN connecting these 2 points, how much does it buy you in terms of security? And like if your attacker is the Great Firewall of China or the NSA, doing this very not targeted like bulk attack versus say an attacker that's attacking your specific node and is okay writing custom software to do it. But I just wanted to throw this in there because it's kind of an interesting question. So I believe there are certain things that if you send, there's certain like packets and like bad transactions and various behavior that if you send to a node, that node's IP will be added to a blacklist. I believe there's like a point system when it hits 100. I know they've changed this recently, or they've changed this a few times. But there used to be things that you could send, and you'd have like blacklist points. And when you hit 100, you'd be blacklisted. I'm not sure when they would back off that blacklisting. But you could reset the connection and then stick your own key in there. Yeah, or stick your own key. You still wouldn't be like Inpath, so these packets would be going out here, but then you'd be like racing those packets and trying to keep that connection there. So maybe you send a reset this way and you send a reset this way. This node doesn't think it's talking to the purple node anymore, so it's just dropping all of its packets on the floor, and then you're like talking to the purple node. So in the past, you would, when we were writing the Eclipse attack paper, you would be more likely to connect to a peer that you had connected with recently than in the past. And so what this would do is that if you had a Longlife connection to someone, they would be more likely to connect back to you, and you'd be more likely to connect back to them. And so it created this cluster of very tightly connected long-life peers that were all connected to each other, and then new peers couldn't even get in because there was all the connections, all the incoming connections were full. And there was another paper that looked at the peer-to-peer network and observed it wasn't actually a random graph, that it had this weird property. And so I personally believe that it was that that most recent behavior that accounted for that weird property. Now that that's been removed, I don't know. No one's done a study to see whether it's actually a random graph or not that I'm aware of. And I don't know if it's the case that, I guess like a way to answer your question would be to look at if long-life nodes have all of their incoming connection slots filled. Because if they do, you probably start to have behavior like that. But if they don't, then like a new peer would just potentially connect to one of them. But I think that's a really interesting question, and sort of studying the Bitcoin network, there's some surprising emergent behavior. So now we're going to talk about off-path attacks. So this is much more what the Eclipse attack paper did. You fill the node's peer table with attacker IPs. The node restarts, loses its current outgoing connections. The node makes new connections to only attacker IPs. So you see this node has been eclipsed by attacker. I'll just go over this really quickly because I'm sure you're all pretty familiar with it. How easy are restarts? Restarts happen. You know there's a new version of Bitcoin. There's some security patch. You either reboot or you don't. In either case, the attacker is happy. If you don't reboot, they exploit you. And I think this should just generally be a principle. The security of the peer-to-peer network should not rely on 100% node uptime. We should accept that we have an attacker that can strategically restart your node. I think that a list of banned IP addresses like probably has some use. A targeted attacker should be able to get new IP addresses. But for example, when Chainalysis was accidentally eclipsing, they eclipsed a bunch of wallets that were connected to the peer-to-peer network that were not actually Bitcoin D nodes, because the wallets only made 3 outbound connections and they didn't have this /16 rule. So Chainalysis, to not do an eclipse attack, had all of the IPs that they were performing this attack from be in the same /16. So they thought they'd only get 1 outgoing connection. But because these wallets didn't implement that rule, they just made all 3 outbound connections to Chainalysis' servers. And so when I first started seeing Chainalysis send me all these like packets and basically do the eclipse attack while I was also doing the eclipse attack, like I was doing it and I was like, oh good. And then the results in the paper are actually worse than they should be, because there was like 2 people attacking. There was me attacking the node and them attacking at the same time. So they were also trying to fill my peer tables with their /16. I looked up their IP address because I had no idea who this person was. And I found on port like 8080 on their IP address that like it was like Chainalysis law enforcement portal login. And then I typed into Google and I saw that there was all of these wallets that had ban lists for it. So I contacted one of the wallet maintainers and I was like, what do you know about this IP address? And they're like, oh yeah, like our wallet stopped working for like a month. And all of our wallet was connecting to this /16, so we just added it to the ban list, and we haven't had a problem since. So I do think ban lists can work, especially when you have like accidental attackers. They were trying, I would presume, but I don't know, they were trying to engage in like network surveillance, and they just accidentally eclipsed some people. But once they got added to the ban list, they continued their behavior for a while until there was it got written up somewhere and then they apologized. But the ban list did actually make it so they weren't able to connect to all of these things. So ban lists sort of do work in this interesting area where it's like, you know, you'd think they'd switch IP addresses, but they didn't.
I remember tweeting about the latest update and someone replied back, oh, it's just like stabbing into the water. It's just so temporary. There's no point.
Yeah.
But I was wondering what your take on that would be.
Yeah, so it's like sometimes things like that can be incredibly effective, and sometimes things like that can be really ineffective. Just an anecdote, similar thing. I had a friend who was at a CTF, and they were trying to like get an exploit to run on a server as part of this competition, and they spent like a good chunk of their time. They're like, we know it works. We've tested on our own systems. It won't work on the other system. And it turned out, and they couldn't figure it out. They like gave up. They couldn't figure it out. And it turned out the reason they couldn't get it to work was that they were using a host name to do the callback. And on that network, they just turned off all DNS. So it like totally stymied them. They didn't even think of that. So sometimes, like from an attacker's point of view, an attacker can instantly be like, oh, I'll get a new IP address, or like not realize what's going on and just like be like, oh, I guess it doesn't work anymore. It's surprising how things can break. I feel like with all of this networking stuff, no matter like how robust the software was, how robust the software is, you always have to be careful. When we were doing the Eclipse attack paper, my advisor, who does a lot of network security work, was like, we have to be incredibly careful. Like all the IP addresses you use to do stuffing have to be like non-allocated IPv4 addresses, and we have to like set up a firewall so that those packets like don't leave. And we modified the victim nodes that we're attacking so they wouldn't send any address packets out for any of the IP addresses in that unallocated range that we were using. And I like at the time I was like, oh no, this is like maybe a little bit overkill. It's good to be cautious, but like, you know, I'm making the code changes and I'm like, do we really need to do this? And then we saw that there was a paper that I think it was Bitcoin over Tor is not a good idea. And in the appendix, they had a attack. And the attack was, if you just broadcast lots of addresses, it'll fill up this buffer in Bitcoin, and then that buffer will get so big that it will crash. But it will also send out lots of IP addresses, and when it crashes, it'll forget about that buffer, and then it will get them again. So you sort of have this rolling brownout effect on the peer-to-peer network. And it was never exploited. And it's in the appendix of this paper. When we were doing this stuff, it was like a month after it had been patched, but we didn't even know it existed at the time. So it was actually really good that we were cautious, because if we had done it earlier and had not been cautious, we could have actually caused some serious problems. And there's, I think the Bitcoin dev chat, if you like look up that paper, there's a thing where someone like notices this in the appendix and like, have we fixed this? And it was like, oh yeah, we independently discovered this like a month ago and fixed it. But I think with all of this stuff, you always have to be really careful, because when you're doing unexpected things to any sort of network, like you can cause like really big disasters accidentally. All right, so this is pure table manipulation of the peer-to-peer network, because outgoing connections need to be in different /16s. The attacker needs at least 8 IP addresses in different /16s. The new and tried table limits the buckets that a /16 can be in. So you have a /16 like this, and it can only be in like, let's say these like 8 buckets. And this is actually a good defense, because there are more /16s than there is room in these buckets. So if you just own an entire /16 and try to attack the Bitcoin network, you'll limit yourself to these buckets. And then also having the outgoing connections in different /16. So you can't just like buy a /16 and then do like a massive attack. You have to have a diversity of IP addresses, which for some attackers is harder. It used to be more of a thing. Like when you get allocations from like IANA or like AppNic or whatever, they'll usually like try to give you a range rather than a bunch of random IP addresses to make routing tables nicer, so that they can like compress it and be like, oh, this AS owns this range, rather than this AS owns this like 1,000 random IP addresses, right? So they will try to do it. It is easier if you're buying in bulk to get them all in the same range. But you can buy like random IP addresses from like different cloud hosting sites, and get different /16s. And botnets are sort of often very diverse in their IP range. Although since they usually target consumers, it's like the IP addresses of ISPs that serve consumers. But when we did analysis, and I actually don't talk about this here, but we did an analysis of IP diversity, and most botnets have like sufficient IP diversity that this doesn't present much of a problem to them. But if a company just decided to attack Bitcoin, right, this would present more of, like using their existing IP addresses, this would present more of a problem. So one of the assumptions these defenses make is that that the node's been running for a while. It has a bunch of honest IP addresses in its tables, and then the attacker shows up. So it's like if this is a timeline, it's like good, and then like evil shows up. Not like evil shows up first, and then good. Because if evil shows up first, they just win, right? Like the reason we make this assumption is not because it's a good assumption to make. Like this could happen just as easily as this, but if this happens, you've already lost. It's much harder to defend against. So we assume this because at least with this you have a fighting chance. So a core assumption is that the IP addresses that you currently have are good, and the IP addresses that you're going to get in the future are bad. Yeah, so by like honest, I mean honestly follows the protocol. But yeah, there could be older nodes. It could be, we're looking at like off-path attacks, but if you think about like on-path attacks, those honest nodes could now be like hijacked by someone else that's injecting packets in there. Yeah, so they could be like, but yeah, they could be like, I guess I'm using the term honest to mean follows like the current protocol, not to mean like good intentioned but bad. Right. So if we make this assumption, one of the defenses which is currently deployed, test before evict, is if you see an IP address in the tried table and a new IP address is going to evict it, test the IP address in the tried table first, and if it's still up, don't evict it. And this sort of has this notion that it's more likely to be good than evil because it's already in the tried table. And so this is deployed in Bitcoin now. And what this means is that if your tried table was entirely filled with honest IP addresses that were online, an attacker wouldn't be able to get anything into the tried table. But that's probably like never going to be the case, both because nodes go offline and also because it would be unlikely for the tried table to be completely filled up with IP addresses. Does that make sense? So another assumption is that the new table is easy to fill up with trash IP addresses. This is because these IP addresses are not announced. These IP addresses are not like tested. So I can just have my Bitcoin node and I can fill an address packet up with a bunch of like crazy IP addresses I just made up that have never been Bitcoin nodes, that will never be Bitcoin nodes, that may be unallocated IP address space, and I can announce them to you and get in your new table. So this argues that the new table is not really a defendable position. Anyone can come along and just like fill it with crap. It does. But if I'm a peer, I could just connect and then just blast a bunch of like nonsense in there, and it's pretty hard to prevent. Or I don't know of any good way of preventing that. So generally, this assumption is that we sort of trust the tried table, and we don't really trust the new table. And so the tried table is really is really what the attacker has to overcome. They can overcome the new table. The tried table is sort of the defendable position. And so what we want to do is we want to increase the number of IP addresses in the tried table to make the tried table harder to take over. Because if you have nothing in the tried table, then it's super easy to take over. So there is a countermeasure that's in Bitcoin called feeler connections. And what feeler connections does is after you've made 8 outgoing connections, you have 8 outgoing connections. Every 2 minutes, there'll be this 9th connection, which is a feeler connection, which will like either pull an IP address from new and check to see if it's online. And if it is online, it'll add it to the tried table. Or it will, if something is going to be evicted from the tried table, the to be evicted IP address will be added to a buffer, and test before evict will pull from that buffer to see if that the feeler connection will pull from that buffer to see if that IP address should be evicted. And so basically we have this situation where stuff in the new table gets tested by the feeler connection and ends up in the tried table. So if we just look at how many attacker IPs, and these are like randomly sampled IPs, so they're going to be like randomly sampled in different /8s. How how many the attacker has, and the attacker success probability. We can see this is just the red line is default Bitcoin, and the blue line is feeler connections. So it's harder for an attacker. An attacker needs more resources, needs more IP addresses. And when we add feeler connections before evict, we get out slightly to here. So you need around 9,000. This probability analysis was done a while ago, back before these countermeasures were implemented. So this is like kind of assumes the spherical Bitcoin. Now that they've been in Bitcoin for a while, it would be really neat if someone could like test this and see what resources an actual attacker needs against the Bitcoin network. Right. So I believe what would happen is that it tries to add, say, like IP1 to tried, but there's something already in tried. There's IP2 is in tried. So IP2 gets added to the like test buffer. I forget what it's called. And the test buffer consists of IP2 and IP1. And then the next time a feeler connection comes along, it will pull from the test buffer. And if IP2 is offline, it will insert IP1 and evict IP2. Otherwise, it will drop IP1. So this test buffer, I think, holds a maximum of like 10 entries. And the feeler connection, if the test buffer is not empty, will pull from the test buffer, and then we'll go back to new. And currently, there's one feeler connection. You could add more feeler connections if you wanted to move stuff from new into tried. An open question that I don't have the answer to, but my intuition is that there's just not enough nodes that accept outgoing connections to completely fill tried, especially because when nodes may, when something is sent into tried, it's mapped deterministically to a particular position in tried. So 2 IP addresses can just map to the same position. It's randomized for each node, but it's the so even if there was exactly 10,000 nodes in Bitcoin that accepted outgoing connections or accepted incoming connections, and the tried table was 10,000 IPs big, it would still have there would still be some empty room.
So deterministic per node, but different for each node.
Right.
So that people can't try to game it.
Exactly. And this was in the Eclipse attack paper, because before it was probabilistic, and deterministic was actually made the attack harder. So to eclipse a node, you need to control both the incoming and outgoing connections. Since the Eclipse attack paper, in the Eclipse attack paper, it was really easy to control incoming connections. You could just make 117 connections from the same IP address, and you totally monopolize incoming connections. This was actually like, I don't know if anyone like tried this attack against the network. I certainly didn't. But one thing that you could have done in that past Bitcoin is just like take every single node that accepts incoming connections and just like fill up all their incoming connections. So when a new node joined the network, they wouldn't be able to make connections to anyone. To defend against that DOS connection exhaustion attack, Bitcoin, under certain circumstances, now allows new incoming connections to evict old incoming connections. And there's a set of rules for doing this. One thing that's interesting about this new rule is that when you evict an incoming connection, you're actually breaking someone else's outgoing connection. So there's a question of whether this is like gameable to make an Eclipse attack stronger, where you can break outgoing connections by getting that outgoing connection to be evicted where it's an incoming connection. I don't know if that makes sense to everyone, because I'm like using incoming and outgoing. It's a little bit confusing. But like this node's outgoing connection is node A's outgoing connection is node B's incoming connection. And maybe if you make a bunch more incoming connections to node B, it'll break this connection because it'll like replace this incoming connection with that incoming connection. So I don't know if anyone's like looked at whether that helps or not. I don't know whether it works or not, but I think it's like an interesting area to study. And then the other question is like, let's just say you want to do this connection exhaustion attack. At some point, you're just like evicting yourself and sort of like locking people out. So to perform this connection exhaustion attack, how many IP addresses do we need? And I don't know if, I certainly don't have any hard numbers for that. And if you were to perform an Eclipse attack, how easy would it be to eclipse the incoming connections given this eviction logic? So I looked at the source code. None of this has been like tested, so this is just from me reading the source code a couple days ago. But this is the rules for evicting an incoming connection. So you create a list of all the incoming connections. You remove 4 IP addresses with a particular /16. So there's just some random /16 that's the protected /16. And you remove up to 4 IP addresses with that. You remove 8 IP addresses with the lowest ping time. And each time you're removing these addresses, this is the list of connections to evict. So you're now protecting those from being evicted. You remove 4 IP addresses that most recently sent us transactions, 4 IP addresses that most recently sent us blocks, and remove the oldest connections, 50% of the list. And then there's this prefer evict setting, and if any remainders on the list have prefer evict, then you evict that IP. If none of them have prefer evict, you select the IP addresses that have the most connections from a particular net group, a particular /16, and you evict the youngest connection from that net group. And so it'd be really interesting to like model this and see like how well this works and like what happens when you make like lots of connections to it, how gameable it is. Maybe it's really robust to attacks. Maybe there's some like clever games you can play with this. I don't know. So this is a net CPP line 857. There's this set of rules. Net CPP 857. But yeah, I also just wonder like how this is like justified. Like a lot of the ideas that have been that people have come up with in this room have been like, you know, like let's make sure the ones that send us blocks, we like keep those connections. So it seems like that logic is in here. Right. Yeah. Yeah. Like if you imagine someone got booted and they connect to another node and you're doing a connection exhaustion attack on the whole network and they get booted from that node. But like only if they're in this like net group. So I don't know, it's interesting. I'd love to see like quantitative models of like how this works and how attackable it is, especially because it allows you to break outgoing connections. If I was writing an Eclipse attack paper, I would totally be focused on like figuring out if I can use this as a tool. This would be like my starting place. But I am not writing a new Eclipse attack paper. Can we use detection as a defense? Well, even if something's detectable, it doesn't necessarily mean that you will detect it or that the system you build will detect it. I definitely think that, I don't know how much of this exists, but it would be really great to have anomaly detection on the Bitcoin network so that if there was something like what happened with Chainalysis, it would be like caught quickly.
When exactly was this?
I think this was 2015, like early 2015, maybe 2014. I don't like at the time I was like obsessively reading the like my Bitcoin D net log file, and I'd added some extra like debugging information in there, and I was like processing those logs all the time. So I was like really looking at it. But if it happened today, I wouldn't. I don't observe it that carefully. I assume some exchanges probably have some anomaly detection. I know at my company we have like a whole bunch of alarms, and they've caught like weird stuff happening on test nets. Yeah, I think just like I don't know if anyone's built anything like that, but I think it'd be really interesting just to be like something funny is happening on the network. All of a sudden, there's now all of these new connections. Yeah. Especially a targeted attack, you're definitely gonna miss that if you're not the target. But something that's targeting the Bitcoin peer-to-peer network as a whole, like some sort of like DDoS attack or some connection exhaustion DOS attack, or I mean, yeah. Also, if an attacker is aware of your anomaly detection, they can try to shape their attack to bypass that. And maybe there's attacks which are really hard or impossible to do subtly, like if you're just gonna go and like connect over Tor and like get a bunch of Tor exit nodes to like spam the Bitcoin network, and like there was this one attack where the attacker wants to eclipse Tor nodes, wants to eclipse people talking to Bitcoin over Tor. So what they do is they set up a Tor exit node that talks to Bitcoin, and then they talk through all the other exit nodes and get those exit nodes IPs banned on the Bitcoin network. So everyone has to talk through their exit node. And then you have like, you can eclipse it. So this is like from a paper from like 2015 or 2016 called Bitcoin over Tor is not a good idea or something like that. I don't know how effective that attack is today. But like you would, in that case, you would notice like all of a sudden a whole bunch of nodes on the network have banned the same list of IP addresses, and you might be like, why, right? You'd want like for the attack to be successful, you'd want to like have a majority of the nodes which accept incoming connections to have banned those exit nodes. Like more, probably for a 50% attack chance, you want 50% of the nodes to have banned them. All right, so there are DNS attacks you can do. So when you, as we already discussed, when you first connect to the network, you don't have anything near peer stable. You have to get IP addresses from the DNS seeders. And so if an attacker were to control some of the seeders, they could try to perform an attack. An attacker could also just control your local DNS server. So if you just happen to connect to a malicious DNS server, which could happen if you were like connecting from like a cafe or something. Someone, I believe, actually no, that was different. Or you could do a DNS cache poisoning attack. And I don't know if anyone has actually like tried this on Bitcoin or looked into it to see how easy it is. And I'll explain this and more. Or you can try the seeders crawl the network to find out what IP addresses to advertise. And you could attempt an attack where you just tell the seeders about just your IP addresses. And I don't know how easy attack 4 would be where you stuff the seeders. I believe the seeders have been designed to be resilient to it, but I don't know if anyone's like in depth attempted to attack the seeders. So this was an attack I did a while ago, which is that DNS can return about 4,000 IP addresses. So most of the seeders were only, the honest seeders were returning 160 IP addresses. And you could have an evil seeder that would return 4,000. So you could use this to, even if only one of the seeders was malicious, they could send way more IP addresses than the good seeders. However, this is fixed now. And regardless of how many IP addresses are returned, Bitcoin now limits this to 256 IPs per DNS seeder for this reason. So DNS is UDP normally, but DNS supports this behavior where you can say, I've got more IP addresses than that, make it like a TCP connection to me, or make a additional connection, and I'll give you the rest. And because, at least at the time I tested this, Bitcoin relies on the underlying OS to do DNS resolution. That just like did that. So I made a malicious DNS server and then sent like 4,000 IP addresses. There's a little bit of that that's already built into Bitcoin, which is when you write something to the new table, you limit the buckets it can go into based on the /16 of the announcement. Yeah, so that prevents like a single IP address from completely flooding the new table, which was like a really clever mechanism. I remember reading it and being like, oh, like at first I was like, why are there these buckets here? Like, what is this? What are these net groups? And then when I like actually figured out why they were there, I was like, oh, that's really smart. So if you control the local DNS server, you could do like direct DNS cache poisoning. So when someone makes a DNS request and the DNS server responds, it responds with this value time to live, which is the also known as TTL, which is how long to store this results on your local machine. So what someone could do is, you're connecting to the Bitcoin peer-to-peer network for the first time from, some Wi-Fi hotspot. Actually, let me try that a second time. All right, let's say you walk into a cafe. You haven't installed Bitcoin on your laptop yet, and you talk to the cafe's like Wi-Fi, and it makes you open a page. And hidden in that page is the like DNS addresses for the seeders, like in an iframe. And so your laptop now makes a DNS query to the local DNS server about who that is. And the local DNS server is like, oh, it's just these IP addresses, and it puts like a 2-year TTL. You're gonna like cache that result later when you do a DNS lookup. I'm not actually. I know Bitcoin has some of its own DNS code, and I know it differs by operating system. So I haven't tested that particular attack, but that is a general attack on DNS that people have done for like malware distribution. So you can sort of like poison someone's DNS cache ahead of time using an approach like that. So when they do start it up, they just have these cached DNS results. Or when the DNS server is looking it up, you could say poison it at this point. So this DNS server will cache things. So if you can inject like packets in here, you can poison the DNS cache here, and then this will announce it to everyone. So if you like manage to poison Comcast DNS servers with the Bitcoin seeders, then everyone who created a fresh Bitcoin node would get the only attacker IP addresses, and you'd eclipse them all. In regular DNS, this stuff is not protected. So as an off-path attacker, you can inject packets. You can like spoof packets. So at least in theory, it should be possible to like cache poison a DNS server. DNSSEC is designed to prevent this and has been somewhat rolled out, but it's not rolled out universally. So there's, I guess the high level from this is there's a whole bunch of really bad things you can do with DNS. A lot of these things are not under your control. Yeah, so you could not use DNS for this. And I believe some other cryptocurrencies don't use DNS. My understanding of the reason that DNS is used is because you only talk to your local DNS server in many cases. And if there was just one server that the first time a Bitcoin node booted up, you requested from, then the access logs to that server would be everyone who runs Bitcoin Core. Whereas DNS provides this layer of indirection that kind of like hides who's asking queries. I don't know how good that actually is from a privacy standpoint. But like even if you don't, like the idea is that it does provide some benefit. It's not like there's just a server out there that's a list of everyone who does it. And so that's why they use DNS versus say like TLS to some server that gives you like a JSON list of all the IP addresses. Oh, all right, yeah. The hard-coded IP addresses. Like how are those actually like how are those generated and how many of them are online? My lab mate was doing these really fun UDP fragmentation attacks for injecting traffic as an off-path attacker and like doing DNS cache poisoning attacks. You just like inject it. You like request it from some like resolver, and then you know it sent out a packet, and you do like a fragmentation attack to like inject your packet without being Onpath or Inpath. Like a bunch of, because it's UDP, it doesn't have the same protections. So one idea to solve this is that you could try to authenticate the seeders, where you, so you could send some of the DNS response could actually be like a signature on the other IP addresses. So like you could encode a signature in like the first like 2 IPv4 addresses or the first like couple IPv6 addresses. And so you could make this like signed data and sort of just shoehorn in signed data over DNS. And since you're already hard coding in the DNS seed, you could also just hard code in a pub key for that DNS seed. Or you could look at like turning off DNS cache poisoning, so you always make a new request. And maybe this is, I haven't looked at the DNS code in a while, so maybe like cache poisoning was turned off. I don't actually know that that this isn't already fixed. But it's an interesting thing to look at. Like you're asking DNS seeds, you should almost definitely not be using whatever cache you have locally. You should at least be going off to your like local resolver. Right. You could actually just call off the DNS through Bitcoin, but almost all applications rely on the OS to do that for you. So I feel like we talked about a lot of this stuff. In general, some sort of like project ideas, things that I think would be cool if people worked on, was like hardening the DNS seeders against attacks, thinking about how to make on-path attacks harder. UDP kind of has some interesting properties for on-path attacks. So like off-path, UDP is usually easier to spoof packets because it's stateless. But if like 2 parties send you UDP packets, like you can't necessarily do these like reset attacks where you just break the connection and the person will drop packets. And then incoming connection logic, like, is there any way to game this? How like optimal is it? Is there some like fine tuning that would make it more secure?